How's it going, guys? So today I am having a mate round, just giving the Proton a quick rinse off. It has been constantly, I know that we Brits love to complain about the weather, but genuinely it has not stopped raining for like the last 5 weeks, and the car just gets absolutely disgusting. As you can see, Proton, yeah, still looking quite fresh, still looking quite nice. It's got different wheels on it to how most of you will remember it. It's got 18s on it now. It's quite difficult to find 18s in this bolt pattern, but I managed to find some, and they look pretty nice. So I'm just going to go pick my friend up and take you along for the ride and show you some bits and pieces that we get up to along the way. Got my T-line door cards here. They need a bit of a wipe over because yeah, they like to pick up sort of dirt and stuff. They're not too bad though. They're still looking really good. The A pillars, I've got the DD AW3s. They have bleached in the sun like really bad. They used to be black and as you can see, one of them is slightly lighter than the other because one side gets more sun than the other side. So it's not really noticeable, but I mean, the amount you pay for those AW speakers from DD, you want them to stay the right colour, don't you? I mean, come on, let's be honest. Alright, let's fire up. A little bit noisy. There is a squeaky belt. Got a squeak auxiliary belt because I actually had a second alternator fitted to this car years ago when I was planning to do like a big loud build in here. I had a second alternator fitted, but it was never hooked up. I never had a regulator hooked up to it. And in the time that I kind of faffed around getting regulator sorted for it and stuff like that, I actually changed my mind and decided not to do a super loud build in here because I like the car too much, and I decided to go with SQ. So that second alternator just sat spinning as a pulley for like years. And it wasn't actually mounted very well. The garage I took it to, they didn't do a very good job of mounting it. So actually, I think it lasted for about 5 or 6 years, and then it actually fell off. Fortunately, it fell off while I was parked up in a petrol station, so it didn't fall off while I was actually on the road, because that would have been a disaster. But I just heard this clunk, and the alternator was sitting there on the floor of the petrol station. So I had to get recovered, and after that I said, you know what, don't put the alt back on, let's just get a smaller belt and go around the pulleys and just leave that off. So it's got stock alternator still, and that's absolutely fine for an SQ system. The kind of system that I'll be running in here is not going to draw much current whatsoever, so stock alt, absolutely fine. However, the auxiliary belt that was fitted, so obviously maybe a little bit of a cheap one, it's a bit squeaky, so I need to sort that out. Okay, let's make a move. Wow, it's a mega bright day today. So I'm sure a lot of you are wanting to know what the sound system sounds like in here. I recently put out a video, if you check that out, of my new speakers from my living room, which are some Martin Logan Electromotion ESLs, and I got the RTA mics out so you can actually hear what they sound like. It's a little bit more tricky in here to get you a stereo image, because I'd have to have the mic so close to the A-pillars here, and it wouldn't really give you a good idea as to how it sounds in the listening position, because the acoustics are so funky in here. Like, to get good bass response, you have to be in the driver's seat here. So I'd probably just use a single RTA mic just to give you the frequency response and not worry about the stereo image. This is the worst toning to come out of, I swear. But this camera that I'm currently using has the worst microphone I have come across in many years. Not quite as bad as that old Kodak EasyShare that I used to use back in the days, but it's very bad. And it's early morning as well, so I'm just going to take a cruise, let the interior of the car get up to temperature as well. We're currently having nighttime temperatures of around freezing, 0 degrees Celsius. So if I go and turn the amplifiers on and start blasting music straight away, with them being Class AB, they're going to warm up quite quickly, and the condensation will form on the heatsink and inside, which is not good. So you want to let the cabin get up to temperature first before you start running your system hard, especially if it's going to get warm quickly. So the interior floor of the Proton is double sound deadened with incredibly thick sound deadening. If I'm honest, I don't really know how much of a difference it made. Where I'm not having loads of bass in this car, the sound deadening kind of mostly helps with bass, and I've got so much interior stuff in here that the mids and highs, the sound deadening on the floor probably wouldn't make a huge difference. So I do have a slight regret for that because it's added so much weight to the car. This car is not a powerful car by any stretch of the imagination as it is. It's a very, very low power, crappy engine in here. It's like really, really low power. So I've added lots of weight in the sound deadening. And these T-line door cards weigh a freaking ton. These are very, very heavy door cards. You can feel it when you open and close the doors. And also I've got the kind of heavy-ish L-ported sub box in the back, and these wheels are heavier than the old ones were. So this car was already slow and is now extremely sluggish, especially pulling away. It really is not a nice driving experience. Doesn't have much poke because it's so heavy and it's such a small engine. But aside from the odd occasion where I would need to kind of quickly get past somewhere or pick up some speed on the motorway, you don't really need huge speed or acceleration driving around the UK. The roads are so tight and compact and there's so much traffic all the time and the speed limits are usually pretty low. Honestly, it's absolutely fine. I mean, look. See how long that second gear was? And that was going slightly downhill as well. It does sound nice though. It definitely sounds like a car that should be quicker than it is. And because it's so slow, you get some nice engine notes for longer than you otherwise would because it takes so long to change gears. Carriageway. So I'm in second, I'm holding it at about 3.5k, let's floor it. Let's see if we can get a good go off the lights here. You'll see how slowly this picks up speed. Literally, I get beat off the lights when I'm trying my hardest by old grandma in her Micra. Don't diss Micras, man. Micras are actually pretty nippy off the line. They have an extremely close gearbox. Way too much wheel spin. Way too much wheel spin. So as you can see, not the most rapid of acceleration, but it does sound very nice. I don't know how much of it will come through the camera, especially with the windows open, but it does sound better than it performs. So I've got to...
Just gonna put these down here, I think. Should be right down there, right?
Yeah, it should be fine. So I can just put them in the back here.
Alright. I'll carry these.
Alright, cool. Okay. So we loaded up with a few bits. Some pieces you'll remember from way back in the day if you follow the channel for a while. Gonna do a really fun thing with a realistic. Got a couple of realistics, both the same ones, and some other bits that you'll remember. So let's make our way home.
Yeah.
And this is probably like Auntie Margaret in her Kia. It's just like chilling, like leaning on the accelerator, and I'm just matching it.
just the turntable now, I think.
So, a few bits I'm doing today. Here we have a turntable. This is a USB turntable, so you can play records on it and you can actually output. There you go, mate. And prepares.
Ah. What the hell's that? Okay.
So with this turntable, outputting its audio over USB as an option, it also has the option for RCA outputs. But because the RCA preamp is right next to the USB interface, there's actually a low-pass filter applied to the whole output to prevent any noise from the circuit that deals with the USB, which has like high-frequency data and switching and stuff on it, from actually making its way into the RCA audio signal. However, as a result of that, it actually affects the high-frequency response of this turntable, of the RCA outputs. So it doesn't sound very nice. So one of the modifications that you can do to this turntable, which is actually documented online, is you can bypass the whole preamplifier stage and connect RCAs straight to the stylus, the needle, and then run your own phono preamplifier. So that's what we're going to do. We're going to bypass that and solder some wires onto that. But if you've been watching my channel for a long time, you will have seen this is the Sony 8 that I picked up off a mate many years ago. This isn't the same one. My good friend here found one of these for sale, and we just had to grab it because I want to measure the TS parameters of this driver and just see what its characteristics are like. Remember how this sounded with the port and also with it sealed. If you were following my channel, you remember that when I sealed the port, it actually sounded much nicer and played much lower. This was actually a relatively nice sounding sub. Didn't go very loud, but it sounded okay. We also have one of these. You'll remember this very well because I had this for years. This is a realistic mono PA amplifier. This isn't my one, this is my friend's one. He has one as well, so we both have one of these realistics. They both have issues. My one, the clipping light and the needle comes on way too early, so I think it thinks that I'm outputting more signal than I am, so it tells me that I'm clipping even though I'm way miles away from clipping, just even with a little bit of signal. Whereas his one, I think your light doesn't work. The light's broken, yeah. So the lamp for the needle doesn't work, so both of them have issues, but it'll be really interesting to actually bench test them and see how much power they make, see if they're roughly similar or not, or if there's any differences in them, because they're both the same amplifier model from the same era, and it'd be really interesting just to see how much power they actually make, what's wrong with mine, what's wrong with his. Right, so this is the turntable, and what we've done is it used to have, obviously, the stylus would go to here, and then those traces just bridge it around to here, and it then went to this preamp board, and this preamp board obviously has the USB on it, and it also had the original RCAs connected to it, and in the circuitry here, like I say, there was a low pass filter to prevent noise from the USB circuit from making its way into the audio signal out of the RCAs. So by completely bypassing this preamp board, we've wired some nice good quality RCA cables with a ground wire straight to the pads here that come from the stylus, so that's now ready for using a external preamp. So this is my good friend here's realistic, much better condition than the one that I have and had, which is this one. So I thought it'd be really fun to compare the power. I'm not sure if I've ever actually properly bench tested this amplifier. I made a video quite a long time ago where I supposedly thought I was bench testing the Realistic and getting the true power out of it, but I actually was using a speaker driver because I didn't know about impedance rise back then. So I was using a speaker driver and using Ohm's law, which wasn't accurate because the speaker was obviously changing impedance. So I'm just going to take a quick look inside my friend's ones here because I think there's a loose component, you said?
Yeah, there's something loose.
So I'm just going to resolder the loose component, whatever it is, and then we're going to power them up, bench test them, see if they're making the same power, and just how much power they actually make. So this is really interesting. I've never taken the top off of my Realistic before, so this is the first time I'm really seeing what they look like inside. Okay, so we have transistors mounted to the heatsink there. Gosh, these are a really weird looking package. I've never seen ones that are that shape and size before. The soldering looks like homebrew, homemade kind of vibes. This will be the board, the amplifier board. Yeah, because look, these transistors are kind of like on a daughter board out from the rest of the circuit. So I'm assuming that's probably the amplifier board rather than the power supply board. The mains wire comes in here, so then it goes straight into this transformer, and then out from the transformer we go into this board. So yeah, this is the main amplifier board. It's pretty empty though, to be honest. Like, it's not really chock-a-block full of stuff, is it? It's pretty bare in there. So it looks like in terms of power, there's Only 2 transistors. So what's the loose component that you noticed? It feels solid on the board, like if the solder had failed, then I'd be able to pull this lead out and it would like come out. Yeah, they seem fine. So these capacitors are probably well beyond their sell-by date, but we're going to leave them in for now and just kind of see what it's doing. If we were to recap this, then yes, these filter caps we probably need doing, but the ones that are going to actually make the most difference are usually the capacitors that are filtering the auxiliary supply voltages for the preamp circuit, because that's where the noise is going to be most likely picked up and injected. So when you're recapping an amp, the ones that probably make the most difference are actually the smaller capacitors, if you can figure out which ones are for the auxiliary supplies. Alright, so you said this hasn't been powered up in a little while.
It hasn't been powered up in months.
So this could be interesting. So he's going to power it up. This is rated for 100 watts. It doesn't say what impedance it's rated into, but on the back it does say that the minimum rated impedance is 4 ohms. So it could be 100 watts into 8 ohms, because that's what they like to do back in the day. Everything was kind of rated at 8 ohms, even though it could do 4, so it might actually do more power into 4. So I've got a 4 ohm dummy load here hooked up, and we're going to throw some sine waves into this and read the output on the oscilloscope and yeah, see how much power this is actually making clean.
Oh, the dial moved.
Oh, yes, because your light doesn't work, does it?
No, it doesn't, no.
So the only way we know it's on is if it makes signal.
It moved, yeah.
Oh yeah, the
yeah,
dial
there you
could
go.
move, yeah,
Nice.
yeah, because there's got no power light, has it?
Yeah.
That should, right, so it is now on. Okay, cool. So I've got the scope hooked up to the outputs here, and I've got 50 hertz going in. So let's just turn up the auxiliary a little bit here, which we've got going, and turn up the volume. Just, oh yeah, here we go. Got a little sine wave on the screen. Okay, cool. Okay, there's a little bit of clip. Do you see that there? Let's just go with this. It's a little bit clipped, but let's see how much power that is. So we have 20.2 into a 4 ohm resistive load equals 102 watts. It's pretty much dead on. I mean, that was a tiny bit of soft clip, so if that was like perfectly clean, that would probably be just shy of 100 watts.
Yeah.
And so that's at 4 ohms. So yeah, this is doing 100 watts at 4 ohms, which isn't that much power. I was hoping it was going to be rated for 100 watts at 8 ohms, and you know, there's going to be some nice headroom at 4 ohms, but no, apparently not. So I've just turned the frequency gen up to 21 kilohertz, 21.6. I just wanted to see what the sine wave looked like, because these old amps generally actually sounded really nice. And on a lot of modern amplifiers playing up this high, you will see the Class AB crossover point, the kind of switchover point between the MOSFETs, transistors. But this looks like a really nice shape sine wave. Now, I don't have a THD analyzer, so I can't tell for sure, but that actually looks really, really beautiful compared to a lot of amplifiers that I've seen in more recent times for 21 kilohertz. That actually, there's no visible crossover point whatsoever there between the transistors. So now, years ago, when I was running my realistic on the Elemental Designs 7kV.2, I was running it at 2 ohms. Now, obviously with impedance rise, especially in the larger box that I had, it would never have seen 2 ohms. It was probably seeing more like 4 ohms. But this amplifier would have behaved like a 200 watt amplifier to the Elemental Designs. My friend here is curious as to see what this amplifier actually puts out with a 2 ohm resistive load. This is a little bit dangerous, a little bit risque for the amplifier, because this is a very stressful environment for it, and it might have overcurrent protection. No idea, I've never triggered any overcurrent protection on these before. So let's see how much power, if any, it might go pop, it makes at 2 ohms. Oh, so it plays it, but then the transformer's probably getting saturated. You can see there, yeah, it's not happy about that. Okay, let's hit it. I'm going to stop the scope screen. Okay, so dynamically, okay, that's just a quick pulse. You can see there it was already starting to clip off at the bottom. So that is 15.84 volts, just as a little pulse. This is kind of more like dynamic power into 2 ohms. equates to not much more, 125 watts. So I think we're safe to say that the transformer in this is the limiting factor there. That's definitely going to be the transformer preventing that from doing any more power. As we demand more current from it, the transformer is just saturated. And yeah, so even if we wire that down to 1 ohm, I don't think we're going to get more. We might even get less power at 1 ohm just because of the poor efficiency of it down there. So yeah, I think that 4 ohms is probably its sweet spot. Or actually, maybe if you've got a driver with a decent bit of impedance rise, you can wire this to 2 ohms. I mean, it's not protecting, it's not blowing up, it's just not really happy about it. It's not doing much power. So I think that you could wire a 2 ohm load to this if it's reactive and if it's rising well enough. But 4 ohms is kind of its sweet spot. We'll see what it's doing at 8 ohms to see if it's much different.
Yeah, let's do it.
Like on paper, it should be 50 watts, but if the transformer is close to saturation at 4 ohms, then it might be more like 75, 80 watts at 8. Cool, so I've got these 2 dummy loads now in series to give an 8 ohm resistive load. So just below clip point is, there you can see it's starting to kind of warble a little bit there. God, look at the that must be. Oh, I'll tell you why it's doing that. I'm playing 50 hertz, right? And the power supply is 50 hertz. You can see the noise on the rails there as we touch clipping. If I increase this to 60 hertz instead, or whatever, see how much faster that is. So if I go down and play 50 hertz, you can see that we're actually in phase with the power coming in from the mains. Really interesting. But okay, anyway. Yeah, that could definitely do with some better rectification on the rails and some better rail caps. That would sort that right out. But anyway, let's go ahead and pause that right there, just at clip point. We are not getting that much more volts. I thought that we might get a few more volts than we did at 4 ohms, but seemingly not. So it seems that the sweet spot is about 4 ohms. So that is 23.65 volts at 8 ohms. We are getting 69.9 watts. So yeah, it is better. It is better than the, on paper, 50 watts. As you double the impedance, you technically would halve the power, but obviously this amplifier is losing some power when you wire it down to 4 ohms in losses. So when we wire it down to up to 8 ohms, we're getting a bit more power than technically we would predict that we would get at 8 ohms, just because of like losses across the traces. The transformer might be close to saturation at 4 ohms, yada yada yada. So 70 watts at 8 ohms, 100 watts at 4 ohms. For its age, not a bad little lamp. Let's see how much power mine does in comparison, and see if it's the same, and see if it exhibits that same kind of like wave on the clipping, and that'll be interesting because that'll tell us a bit about the health status of the capacitors perhaps in these amps. Okay, now we have my realistic, so let's power it up, make sure it actually comes on. Yep, my illuminated display works, but my clipping and the needle doesn't work. Your one actually was working nicely. I can see the needle going up and down perfectly. So let's go ahead and have a look at the scope screen. So we're wired to 4 ohms, so we're going to test the 4 ohm power first. Okay, cool. There we go. So we have, oh, hey, that's a bit more voltage than yours at 4 ohms.
Really?
Yeah. Unless I've done this wrong. Oh no, hang on. Are we still at 8 ohms?
Wait, but there's more voltage, what?
Oh no, we're still at 8 ohms. Okay, I thought I had wired it to 4 ohms. Okay, fine, let's do 8 ohms. So this is the 8 ohms. So that is actually exactly the same. Pretty much, like by tolerance. Like that's 23.89 volts mine did, and yours did 23.65 volts at at 8 ohms. So it's pretty much exactly the same amount of power at 8 ohms. That's fun. So that was the 8 ohm test. So yeah, the same power at 8 ohms. Now we're at 4 ohms, so let's try this again. Okay, so yeah, we're getting literally exactly the same power. Yours was 20.2 volts, mine's 20.14. So yeah, it's exactly the same power. It's like literally bang on 100 watts. So yeah, they're doing the same power. So I did also see that kind of warpling effect on the rails, so that might just be how they're designed, or the capacitors may just be all needing replacing and stuff like that. So yeah, the realistic was not underrated and it was not overrated. It pretty much did the power that it said on the tin. So one thing that might be quite interesting and fun to do actually is, because we've got 2 of these identical amplifiers and they're performing identically, as you saw on the scope screen there, they actually do play up to 20 kilohertz like really cleanly. There seem to be quite a nice at least by the scope anyway, sounding amplifier, provided you keep them well away from clipping. So it might be quite fun to hook these up to the Wharfdale speakers, which are kind of period correct-ish. They're like old speakers and old amps, and have one of these amps per speaker. It's like a dual mono stereo setup. Yeah, might be really interesting to see how they sound. So this is a really weird one. This is a Yamaha AS201. So on the back of it, right here, at the terminals, it says when using speaker A, output only, the minimum rated impedance is 8 ohms. When using A plus B, because they're parallel, the minimum rated impedance is 16 ohms. However, you've just checked the manual online, and it has a rating down to 4 ohms and 2 ohms.
Yeah, it's super weird.
So, yeah, the manual does rate it to 2 ohms minimum, so yeah. I guess we could try it, but the back doesn't say that on the actual back of the unit itself. So let's get it powered up and see what it's doing at 8 ohms per channel first. So on the back of this, it says it consumes 175 watts. So we've got 8 ohms per channel hooked up, and both channels playing and loaded. So this is doing, if we go, pause that, this is doing 2 times 32.5. That one's a little bit higher, 32.9. So the channels are slightly different by 0.4 of a volt. So we can take the higher one, 32.95 volts into 8 ohms, which is 32.95 into 8 ohms. 135 watts per channel into 8 ohms.
That is very underrated then. It's rated at 100 into 8 ohms. So
wow, yeah.
Pretty impressive.
It's doing alright. It's quite nice, to be fair. That's, well, it's tons more than the realistic.
Yeah, way more.
Like, way more than realistic, even at 2 ohms.
Yeah.
Yeah.
Not bad.
And it's doing it twice. It's doing it twice.
How much was the consumption again on the back?
175. So it's actually consuming more than it's rated to consume at the moment. Maybe the consumption rating on the back is for average music program, whereas this is just a pure sine wave. So that's definitely, I mean, 135 times 2, that's like 270. That's at the outputs, and then it will consume from the mains after efficiency. So it's probably consuming like 300 and something watts. Yeah. So it's consuming, yeah, definitely consuming over 300 watts. We could rate that if I had one of those plug watt meters, but I don't have one of those. So. Right, now we've got 4 ohms per channel, so I'm interested to see how much power this does. There we go. Okay. Wow. Okay, 26.21 volts RMS, 26.5. So we're going to go 26.5 volts, which is 26.5 volts at 4 ohms times 2, 175 watts per channel at 4 ohms. So, wow.
That's very impressive, actually.
That's quite a lot of power. Yeah, not too bad at all.
That's both channels, right? Loaded?
Both channels loaded,
wow,
yeah. Both channels loaded, both channels playing.
Crazy.
Yeah, that is pretty nice. It's like 350 watts RMS if you were to bridge it into a sub.
That's pretty crazy.
You could run a nice indoor sub off this if you bridged the channels, yeah.
Yeah.
At 4 ohms. Not bad. Yeah. Do you want to see if it can do 2 ohms, or do you not want to kill it?
Yeah, let's do it. I don't care.
You sure?
Yeah, whatever.
2 ohms per channel?
Yeah, let's do it. It's fine.
Okay. Okay, now we're at 2 ohms per channel. Let's see what it does, if anything. Well, that was quite a decrease in voltage there. You can see just a tiny little bit of soft clip there at the top. So that was 18.73, and remember, I'm just kind of pulsing this a bit, so this is kind of more like dynamic power, I guess, because I don't want to hold it playing into a resistive 2 ohm load for too long, because if we can avoid killing it, then we'll avoid killing it. But this is still quite impressive for it. So into a 2 ohm load, that was 2 times 18.73, which is the same power, 175 watts.
That must be the limit then.
That must be the limit of the transformer, thereabouts. Yeah, so we're not getting any more voltage out of it than that. But it's impressive that it can at least play down to the 2 ohms. So yeah, pretty wild. You could bridge a 4 ohm, like a single voice coil 4 ohm car sub, because that will be reactive, so I have a bit of impedance rise as well. So that will help out. You could run that bridged at 4 ohms on the 2 channels, invert the phase of one of the channels, and that would actually be quite a nice, relatively powerful indoor sub setup. You know, just cheap integrated amplifier for running a sub indoors. Most of those single 4 ohm subs are only rated for like 300, 350 watts RMS anyway, so that'd be a good, perfect match actually. So now we're going to test the TS parameters of this. This is a LTAX atomic driver from a built-in, from a home theatre subwoofer with a plate amplifier.
Yep.
We're just interested to see what the TS parameters are. So I've got my Dayton DATS V2. I'd love a V3, but the V2 is what was out at the time. So the Dayton DATS V2 is capable of measuring TS parameters of a driver. You do need to give the program some information, like the size of the driver, the piston diameter. Also, if you want to measure the VAS, you need to either know the MMS or MMD, or you need to add a mass to the cone and let it run again to figure out the change in FS, which will then be able to calculate the VAS for. So we're going to see if we can get some TS parameters off this, just to see what kind of driver it is, what kind of box it likes, whether it's actually in the right box from factory or not. So if you don't have a DATS V2 and you want to know what the FS of your sub is, if you're just curious to see what the resonant frequency is, then you can actually take a phone app. This is actually an Android app called Spectroid, and it just gives you a waveform output of the audio that the built-in mic is picking up, and it gives you a pictogram here of the audio so you can see it. Obviously phone mics are not necessarily particularly flat across the board, however they will pick up a frequency if there's a frequency there. So you can hold your phone above the speaker, give it a tap on the surround, and the peak there that comes up will be your FS, 47 Hertz. Don't know if you can see that there on the screen. It was 47 Hertz was our peak there when we were tapping the driver. So I'm going to see how accurate that is and run the TS parameters and see what the resonant frequency is via the DATS. So if we do a impedance sweep, measure through our parameters. Okay, so we have resonant frequency of, look at that, bang on, FS 47.1 Hertz.
Wow.
So that is if you want to know the FS of your sub, then yeah, you can just use that method. There is a bit of a funky bit going on there. I wonder if that's just because of the surface it's on. So I'm going to hold the driver in my hand just to see if that makes any difference. Okay, yeah, let's clear that up a little bit. So the surface that you measure the drive on does matter. If you've got it on a bouncy surface that has any sponginess or springiness to it, that will actually affect your readings a little bit. So best to have it on a solid surface. My hand probably wasn't the best there either. So now we've got most of the parameters, but we don't have the VAS, and we don't have the... Yes, we don't have the VAS or any of the parameters like the MMD, MMS, or anything like that. So we need to tell it the piston diameter, which you can do by taking a tape measure, and you want to measure roughly from the inner third of the surround to the inner third of the surround. So in this case, we've got a piston diameter of 7.5 inches. Okay, so we can tap 7.5 inches into piston diameter up here on the screen. And now these are the methods which we can use to calculate the VAS. We can do a test box method, so we can put it in an enclosure of a known sealed volume size, and we can run the test again and it will work out the VAS. We can add some mass to the cone and it will work out the shift in FS, or we can tell it if we know the weight of the AMMD or the MMS, and we can tell it that and it can work out the VAS from that. We don't know any of those things, but what we do have is a little bit of added mass. So I'm going to go ahead and whack some weight on the cone and see what that does. So for the added mass, we've got a capacitor here with a bit of blue tack, because you don't want it bouncing around on the cone, and that's 46 grams. So we add that to DATS V2 software, added mass method, 46 grams, and hopefully that's enough to change the FS enough for the program to be able to work out the VAS. If not, we can just add some more weight until it is. Roughly stick our mass to the cone there so it doesn't move while we test. Hit measure VAS. Added mass was less than recommended for this driver. No, so we need a bit more mass because it didn't change the FS enough. This is 64 grams, so let's hope that that's all right. Ah yes, there we go, 64 grams was just fine. So now we have a measurement of the VAS, which is 0.635 cubic foot. Cool. So with that information, with the drivers now, we have all the information of the driver that we need. We can go ahead and export that as, I'm going to export it as Clio formatted data. We're just going to call this LTAX. So we can now go ahead and import that into Basebox Pro 6. So if we import that file that we just created, so I've imported the parameters into Basebox 6 Pro, and as you can see, it's BB6 leans it a little bit more towards a closed box. It's kind of in the middle though. You can't always take this. This doesn't necessarily mean a driver should only be used in a closed or vented box, but this gives you some indication as to what the driver is like with its parameters. So as you can see, we've got a QTS of 0.6, QES of 0.7, QMS of 10, quite a high FS up there, and the efficiency is pretty bad at 86% at 1 watt SPL. So let's go ahead and accept all of these, and now we can try it out in various different boxes. Now if we've taken some measurements of the box that you had, we could take a we could kind of take a reference of what the box it's in to start with is, but we can play around with different vent volumes and different enclosure volumes and vent sizes and see what works well for it. So just to start with, I've thrown it in a 1.5 cubic foot box with a 4-inch aero port, 25 inches long, which tunes it to just under 30 hertz. And as you can see, this is the response graph. So even with our 30 hertz tuning here, the actual F3 is nowhere near that. The F3, which is, it's kind of 3 dB under its peak, is way up at 37 hertz. And that's just because this driver has a really high FS and not particularly strong motor force to coil relationship. So it's not really ever going to do so nicely in a low tuned ported box, just because it doesn't have, it's not the right kind of spec driver for that. If we tune it up a bit, if we change the port tuning to, I don't know, say 43 hertz instead, which is probably nearer to where it's actually tuned for. So a 4-inch port, 10-inch long, tuned to 43 hertz, and change the color of this graph so you can see what it looks like instead. You can see there that looks much nicer. My phone ran out of battery, but you can see that it's doing way more output, even up as high as 20, 30. So 30 hertz is about the same, even though we're tuned much higher. 30 hertz is about the same, but being tuned up higher, more nearer this driver's FS, we're getting much higher output at around tuning, and that's going to sound much more transient and kick bassy and kind of musical. And this is never really going to want to play lows that nicely. If we seal this box off instead, keeping it at 1.5 cubic foot, we could go down to 1 cube and doesn't make a huge difference, but just 1.5 keeps the low end roll off a bit shallower. And we plot that one just as a sealed box. You can see here that yes, although we get a bit less output across the board, it actually doesn't perform too badly. You can see here I've kind of guessed the X max would be about 12 mil on this sub. So with this sealed box, even at 1.5 cubic foot, giving it 250 watts, we'd actually only be reaching our maximum excursion about 10 mil. So we could probably even give it like 300 in the sealed box. And it would be at roughly X max there, and do quite good output, whereas in the ported box, under like when we get to sort of like 30 on the sort of subsonics, like the lower frequencies, we would massively reach high excursion as the box unloads. So a sealed box might actually do quite well with this sub. Memories with this old sub messing around in the bedroom years ago. One interesting thing you can do with DATs. Now, the DAT system is designed obviously to measure TS parameters of a free air driver. However, if you run the DAT sweep while it's connected in an enclosure, because it does an impedance sweep and measures the impedance sweep, you can actually work out the box tuning frequency really easily without having to do any measurements and stuff. So let's run an impedance sweep, not a free air parameters test because we're not doing that. So we just want to see an impedance sweep of this. And the impedance sweep will give us 2 impedance peaks and this valley here. So naturally, with the box tuning frequency, where the box is tuned at, it will hold the cone of the woofer still and load the cone, therefore reducing excursion, therefore reducing the impedance rise. So the box tuning frequency here is going to be about 55 hertz. And this big impedance spike is where the box is unloading, and the maximum impedance, the kind of maximum excursion that we'd see if we played free air test tone about 22 hertz, with the box tuning being at 55 hertz, roughly there or thereabouts, where we'll get the least excursion and the most air out of the port. And then we have the box unloading again as we get up to the 75 hertz mark there. Now with a ported box, it doesn't necessarily unload per se on the higher frequencies. The port just becomes ineffective. So we have a spike here, which is where the woofer will be moving very happily and freely at 76 hertz. Cool, so yeah, 53 hertz is pretty high for box tuning. Let's try this again, but let's seal the box. Take that off. Workshop rag in there. There we are. So if we run the impedance sweep again, what should happen now is I'm predicting that there should only be one impedance spike, and that will be around FS, I think. Okay, so we've got one impedance spike. Whether it's around FS or not, we're not sure, because obviously we have an air spring in the box that is working with the suspension of the woofer. But yeah, with the sealed box, we have an impedance peak at 52 Hertz. So that is also going to be where this box will perform quite well. But yeah, interesting. Now let's remove the driver from the box and measure the free air parameters and just see what the free air, FS and the rest of the TS parameters of this old Sony driver is. Okay, so out of the box, what is the free air parameters going to be? What's the FS going to be? Okay, so the FS is quite a lot lower, as I expected. We've got 29 Hertz FS. Now, from an 8-inch driver like this, it's got a home theatre thing, that is actually a pretty nice low FS. Often these things can be, you know, well, even your driver, your one's what? The FS was like 40...
Almost 50.
Almost 50 Hertz. So this is actually a pretty nice low FS driver, and you could make something quite nice from this. Let's check the rest of the parameters, though. I'm going to need to get the added mass method for the VAS. Let's get some blue tack. Now, we shouldn't need as much added mass for this driver as we had for your one, so I'm expecting a capacitor will be fine. 55 grams in the added mass field, and we need to measure the piston diameter of this driver, which is 6.25 inches. Add the mass to the cone, measure VAS, added mass method, and we have our full parameters now. Alright, so let's export these and bring them into BB6 and see what it says. Alright, so I've whacked these parameters into Basebox 6 Pro. And what's interesting is that back when I was a kid, I noticed that this sub sounded way better when I sealed the box off, like we've done here with the towel or something. BB6 actually is like, yo, this is a freaking closed box driver. We've got a QTS of 0.6, QES of 0.7, and QMS of 4.7. So a low QMS, a low FS. That is, yeah, makes perfect sense and explains why this did actually sound really nice to my ears, at least as a kid, in the sealed version of this box. So let's go ahead and throw the rest of the parameters in here. It's probably got like, I don't know, 8mm X max. It's really freaking not that great. The efficiency is horrendous, 81 dB at 1 meter. And this is probably like, I don't know, a 50 watt driver. Let's be realistic. No pun intended. Let's now go to box and let's have a look. And let's just throw it in a closed box first at 0.3 cubic foot, for example. And we're going to go for minimal damping. Actually, typical damping on this one. So yeah, 0.3 cubes, sealed box. What do we look like? We have pretty flat response, like down to 60 Hertz, and even 50 is not bad. The F3 of this setup says that it's 48 Hertz, which honestly is not that bad for this tiny little home theater driver in a tiny sealed box. That would be absolutely fine. You compensate with this with a bit of room, room lower frequency bolstering and a bit of a low pass filter that's set to around here to kind of emphasize these lower notes would be absolutely fine. What happens if we put this in an oversized sealed box at 1 cubic foot instead? With a 1 cubic foot box, obviously we can send less power to the driver because it will reach excursion limits sooner, but as you can see now, the F3 has gone down to 40 Hertz and we're getting still very usable response all the way down to 30 Hertz. That would play 30 Hertz just fine in a big sealed box, but the cone displacement, as you can see in the larger sealed box, is much higher. But if we're only feeding it with 50 watts, it's still only 8 mils of excursion in the 1 cubic foot box. So yes, a nice big sealed box would do this quite nicely. What about if we ported it? Let's go for a 0.7 cubic foot ported box. Let's give this a maybe a 2.5 inch port. Let's make it be about 20 inches long. We're going to lock vent dimensions. Okay, so we now have a tuning frequency of 29.6 Hertz, which is fine. That's nearish to FS. So if we change the color of the graph again, we should get an output. Let's have a look. So, okay, cone displacement is now much higher. We have 15 mils, but that is when the box is unloaded. You can see here 10, 20. So at 25 to 30 hertz, we're actually loading the cone nicely and keeping excursion low. The cone only unloads under, say, 22 hertz. Not a problem. We can high pass that. Let's go down to here. We can see that the response of this ported enclosure is way better. Okay, actually, yeah, that's actually pretty nice. We actually have a really good bump in output at 20, 30, 40. We have a decent bump between 30 and 40 hertz there, and even though this box is tuned to 29 hertz, we actually have a decent response way up at sort of the 40-50 range, and still more output below the 35 hertz range. So this will actually work pretty well in a vented box as well. However, in the vented box, the group delay is all over the place compared to the seal boxes, as to be expected. So if you want low group delays, seal box. If you want a bit more output, then a ported box would be fine. And the cone displacement is well under control in this 0.7 cubic foot ported box. If we went bigger on the ported box, let's just throw in a 1 cubic foot box, screw it, why not? And let's tune it not quite as low as that. Let's actually increase the vent area a bit. This is a 3-inch port for an 8-inch sub, is a little bit on the wide side, but that's fine. Let's go ahead and plot this one now. This is a 1 cubic foot vented box. The excursion actually is still relatively controlled. It's not really reaching crazy limits here. We're still under like 8 mils, but the output is even better, is even more pronounced on the lower frequencies here. This pink line, we've got much less output on the lower side, roughly similar, actually a little bit less output on the high frequencies because it's a larger box. So yeah, pretty interesting stuff. This driver would actually be a really nice little driver for a home theater thing. You could chuck it in a seal box and it would work nicely. You could chuck it in a large ported box, and provided you keep the excursion under control, it would actually be alright. We're now just having a nice listen to the Martin Logans. I've towed them out slightly. When I first put them in, I had them angled directly to the listening position, which apparently is not what you're supposed to do. You're supposed to have them towed out so that you're looking at the inner third of the panel, and it made a big difference for me. Sounds good?
Yeah, it sounds so good. Brilliant.